Il y a tout genre de lolo, les babouches et les pointus.
Okay, good. So we had this référentiel absolu R OXZ, OXYZ plutôt. Dans le plan OXY, une particule M est assujettie à se déplacer sur une tige spirale. Et on avait, ou bien on a OM égale A exponentielle de phi suivant euro, and we have phi étant l'angle entre I et euro. En plus, on avait une particule M0 se déplace dans le plan, dans le même plan. And OM0 is equal to A suivant euro. So we have our M0 there, M0 is there, and OM0, which is this distance there, is A, and we have our M there, we have our M, which is there, and we have OM from there to there being equal to A exponential phi suivant euro. That means euro is in this direction, as you can see. And what they're telling us is we have this point M, it's been displaced on this tige, and it's also rotating around the vertical axis, which is supposed to be the z-axis. It's rotating like that, and it's rotating with an angle phi, because they're telling us phi is the angle between I and euro. So phi is somewhere here. Okay, so if we have this particle M rotating around that like that, it's rotating, forming an angle phi. And so when we'll be dealing with angular vitesse, when we'll be looking at the vector rotation, omega, the angular vitesse angular for M, we'll be dealing with phi, because M is rotating around the z-axis with an angle phi. That means the angular vitesse is going to be the rate of change of phi, which is phi poids. Quelque chose à noter. And then when you're dealing with such questions where you have changement de référentiel, you have two referentiels, you have one référentiel absolu et on a un autre référentiel relative. You first have to identify which one is your referentiel absolu, referentiel fixe. So here we've been told it's R, O, X, Y, Z. Okay, this is how you respond to these questions in mechanics. These are the steps you take. You are given your question, you go through the question, you identify the referentials that you have. Okay, so we have this first referential here, R, O, X, Y, Z, which is this one. We have our Y there, we have our X, and we have our Z, although not being shown in the figure, but it's the vertical axis. So imagine it as coming out of the screen like that. Yeah. So we have this one as our referential absolute. We take note of that. And then we also have here, we have OM being equal to A, E, phi, euro. Okay, so we have euro in that direction. That means le point M est repéré par this other referential, which has rather euro in it. And we know euro goes with euro, E, phi, and K. So we have this second referential, which is going to be our referential relative, okay? And we've been told here, soit R1, M0, origin, and M0 is there. Euro, E, phi, K, le repère relatif. So this repère relatif est un mouvement par rapport au repère absolu, au référentiel absolu, rather. So we have this M0, euro, E, phi, K there. It's going to be moving also, it's going to be rotating like that, or being translated like that, but it's just making a movement par rapport à ce repère absolu. And so when you will be solving your questions, you have to have this in mind. So we calculated la vitesse relative. La vitesse relative, c'est le mouvement du point M dans le repère relatif. The movement of this particle M, or this point M in the repère relative. So that means we are in this repère there, R1. For the vector vitesse relative, we are working there. That means the origin we'll be working with is not 0, but it's M0, because we are in this repère R1. So our vector position is going to be M0, M. So M0, M. And we are going to differentiate that in R1, OK, because we are calculating repère, vitesse relative. C'est dans le référentiel relatif ou dans le repère relatif. So we are going to derive the expression M0M in R1. We looked at this yesterday, sorry, not yesterday, but last week, and you will get your vitesse relative. Then vitesse d'entraînement. Vitesse d'entraînement now, they are asking us to study and to find the expressions for the velocity of the repère relative with respect to the repère absolu, how the repère relative is moving. Okay, so we have our repère relative being there because its origin is here at M0. So as I said, we have a translation. It can be translated on this T's like that, and it can also rotate around at an angle phi like that, just like the point M here in this case. So when we are calculating our vitesse d'entraînement, we are first going to take note of the translation, and the translation is just going to be the movement of the point M0. So we'll use the vector position 0, M0. We are going to derive that expression in R this time around because we want the movement of this point with respect to le repère absolu. So we are going to derive 0, M0 dans R, and we get our translation. Then we are going to calculate our rotation, and we are going to use omega vectoriel O M0. We have these expressions in the polycopy. You'll find them, and you get your vitesse d'entraînement. Then after you get your vitesse d'entraînement, you calculate finally your vitesse absolue, which is just going to be the sum of the vitesse relative and the vitesse d'entraînement. And then you will get the entire vitesse over the particle M in R. Okay, it's just like we have decomposed the movement. We want to study the movement of this point M in le repère R. Okay, so it's like starting from there up to there. So instead of going directly from this point to that point, we decompose the movement. Okay, we bring in another referential, then we decompose the movement. So we first study the movement of the point M with respect to this referential R1. So it's like we're just starting from there up to there. So we study the movement there. And then finally, we study the movement of this referential R1 with respect to the referential R. So which is now going to be the movement of this point to that point there. So it's just like we have decomposed the movement. Then finally, we add the two and we get our vitesse absolue. Then today, that was just a quick recap of what we looked at last week. Today, we are going to continue avec les accélérations, when we'll be calculating accélération relative, accélération d'entraînement et accélération Coriolis. Vous avez tous ces expressions, vous les avez plutôt avec vous dans le polycopie. Si vous avez révisé ce polycopie, je pense que vous n'aurez pas de problème. OK? So, les accélérations, on a les expressions ici. Attends. OK, here. So, we have accélération de Coriolis ou accélération complémentaire. The formula is here. We have 2 multiplied by omega vectoriel. Vitesse relative. Ça, c'est la vitesse relative. Because you have R' there. R', c'est le référentiel relative in this case that we have in the polycopy. So when you have vitesse de M par rapport à R', ça c'est la vitesse relative. So that's the formula for acceleration Coriolis, and that's the formula we are going to use in the question above. Then we have our accélération d'entraînement. This one is longer. Okay, so you first calculate gamma de O' par rapport à R. Remember, in the vitesse d'entraînement, we calculated V de O dans R, or the M0 rather, in the question. So here we're just going to derive that expression again, okay, to get our gamma, tout simplement. Then next up, it's plus the derivé of omega, okay, derivé of omega par rapport au temps vectoriel O'(M). In the question that we have, this is going to be M0M plus double produit vectoriel there. Okay, we have omega de R' par rapport à R vectoriel entre parenthèses, omega R' par rapport à R vectoriel O'(M). I already explained these. These are just the expressions that you have in the polycopy. And these are the expressions that you're going to use to answer the questions above. So you have to know these expressions also, okay? These formulas, you ought to know them. So, on passe à la correction, ok? Passe à la correction. Exercice 4. Ok. Voilà, c'est ici. Ok, so, question 3, gamma. Gamma de M par rapport à R1. L'accélération relative. So, l'accélération relative is simply the derivative of the vitesse relative still in R1 because you have vitesse relative is the vitesse du point M dans le repère R1 et ça veut dire que même l'accélération relative, c'est l'accélération du point M dans le référentiel R1. So we're still working in the referential R1. And this is a trick that you need to, a technique or a trick or a fact that you need to know in Mécanique du point when you're solving which referential you are working in. You might get the question completely wrong if you get the repairs and the referentials wrong. You have to identify correctly which referential you are working in. So when they tell you vitesse relative, accélération relative, repère relative, you have to be able to identify ce repère relative that they are talking about. So here we'll be deriving le vecteur vitesse du point M dans le repère R1. We already have the expression for the vitesse de M dans R1. We calculated it last week and it gave us this A phi point exponentielle de phi suivant euro. Sorry, I didn't write this properly. It's supposed to be suivant euro. In first year, I used to, you know, in class when you're a bit confused, sometimes you end up copying the wrong things. It's supposed to be euro. I wrote the solutions in my first year, so please excuse me. This is supposed to be euro and not exponentielle e à la puissance rho. Ça n'a pas de sens. Let me just. Like that, supposed to be like that. Euro. So we're going to derive this expression. So what you need to do here now is to identify the variables that you have with respect to time. Parce que on dérive par rapport au temps ici. So we need to find or to identify the variables that we have, the terms here that are varying with respect to time and those that are constant, we identify them. Et on se débarrasse de. Donc, on commence. So we have A. Is A varying with respect to time? It's an open question for you guys to answer. A. Is A varying from the question that we have?
No.
A is constant. And you find that it's even written in the question. In the question there, it's written, if I go to the question, here, they said, okay, it was in the other question, not this one, but even in this question, R is constant because R is simply the distance from this point to that point. It's not changing, so it's fixed. It's in the other question where they told us that R was constant, but in this one, they did not specify, but you can just see from the figure that R is fixed. So it comes back to being able to interpret diagrams also. And then we come to phi point. Is phi point varying or is constant?
I think this one is varying.
Okay, correct. Phi point is varying. And exponential de phi, varying ou bien constant?
It's also varying.
Exponential phi is varying. And then euro, finally, euro. Is it varying or is constant? Knowing that we are in R1, we are dans le repère R1. Est-ce que euro varie dans R1? Is euro varying in R1?
That one I'm not sure.
We looked at this one last week when we were calculating vitesse relative. It's just up there in the solution. There's even an explanation on top of it. We said euro is fixed. It's fixed in R1 because that's the repère it belongs in. So it's not moving, it's fixed in that repère. Euro is going to become varying when we go out of R1 and we start doing our calculations in R. In R now, the repère R1 est en mouvement. Okay, R1 is moving with respect to R. So that means euro is only going to be mobile when we're looking at it from the perspective of R, or when we're studying it in R, le repère absolu. But if we are in R1 itself, it's not going to be moving because it's not moving with respect to itself. It's fixed in R1. Okay, so euro is going to be fixed in R1. Okay, so as I told you, you just need to identify which repère you are working in and what rules you are going to apply in that repère. If you get it wrong with the repère, you risk getting it wrong with the entire question. So we've identified two variables here, phi point and e phi, and they are all linked by the product. So we're going to use the product rule. And since we only have two variables, we are going to have an answer with a sum of two terms. So we keep our a constant out there. We are first going to derive the phi point. When we derive phi point par rapport au temps, it's going to give us phi 2 points. Okay, so it's going to be a phi 2 points, e phi suivant euro. Sorry, not e phi, but exponential phi suivant euro. Then after deriving phi point, we're going to come and derive exponential de phi par rapport au temps. So when you derive exponential de phi par rapport au temps, you'll be deriving the power there with respect to time. It's going to become phi point. So when you derive the power there, you multiply the entire expression with that derivative that you get. So finally, the answer is going to be a phi point carré, because we have this phi point there, and we have this phi point we'll be getting from there. Then when we multiply it with all of this, we'll have phi point carré exponentiel de phi suivant euro. So here we can factorize a and exponential de phi like that, and we'll have in the brackets phi 2 points plus phi point carré suivant euro as your vitesse, or sorry, as your gamma relative. Okay.
Oui.
And then notice something, is that in your gamma, you have phi 2 points. Phi 2 points. This is showing you that you have derived twice. And as you know, the acceleration is what? It's the second derivative of the vector position. So in the acceleration, you are bound to have second derivatives, as we have in this case, the phi 2 points. When you're calculating vector vitesse, you mostly have first derivatives like phi point, theta point, rho point, etc. But when you start calculating the acceleration, you'll be getting second derivatives also, like phi 2 points, rho 2 points, theta 2 points, et tout ça. It's just showing you that, you are now calculating the acceleration and you are dealing with second derivatives because you are deriving twice now. The next question is asking us to calculate accélération d'entraînement. I was just from showing you guys the formula for the acceleration d'entraînement. Sure you have it in mind. Okay, so on avance. So accélération d'entraînement, you are first going to calculate the acceleration of the origin of the repère. As I told you, accélération d'entraînement, c'est le mouvement, or it's the movement of the repère relative with respect to the repère absolu. How the repère is moving around or with respect to the repère absolu. Okay, so the first thing you'll be doing when calculating your accélération d'entraînement, you first calculate the accélération of the origin of the repère relative dans R, le repère absolu. That's why we have M0 par rapport à R. So we'll calculate the acceleration of the origin of the repère relative. The origin of the repère relative is M0. We already identified this one. Dans R plus the next term is omega point. Okay, this formula you just know it. Omega point vectoriel M0 M. But not just knowing it, but you also know how to get to this formula. It's there in the notes. The explanation is there. You just use formula the ball and you'll get to this point. So after you know how to get to this entire formula, then you can just memorize the formula and continue using it there on. The reason why I'm recommending that you learn how to get to this formula is in the case where you forget the formula in an exam or somewhere important. That way you won't be blocked. If you forget the formula, you just derive the formula and get there. If you can remember the formula well and good, you use it and you get your marks. So the next term is omega point. So you just derive the vitesse angulaire vectoriel M0 M, vecteur position, dans le repère relatif, plus le double produit vectoriel, you have omega vectoriel M0 M, vecteur position, dans le repère relatif. So we have three terms here that we are going to calculate. We are going to begin with gamma the M0 dans R. So this one, gamma the M0 dans R, is just like the derivative of V the M0 dans R. And we calculated this in the second question. When we were calculating vitesse d'entraînement, you'll find it there. We calculated vitesse d'entraînement. We calculated V the M0 par rapport à R, and we got this phi point, phi. So now we are just going to work with this guy here. So again, I'll ask you guys, what are the varying terms in this expression? Considering the fact that we are working in R, le référentiel or le repère absolu, what are the varying terms here?
Here I think phi point and the other one, the last one, they are varying except for A.
Okay, ça c'est très bien. C'est très bien. You guys are following then. I'm encouraged and impressed. So here we have two varying terms. We have A, phi, sorry, not A, but phi point and E phi. Two varying terms. E phi is varying because we are dans le référentiel absolu, le repère absolu. So E phi is varying this time because E phi belongs to the repère relative, and the repère relative is moving with respect to this repère R that we're in. So meaning even this E phi is going to be mobile, it's going to be varying now. So we're going to derive this expression in R, okay? So we have our R as constant. We can just take it out of the derivative because it's not changing anything. Then we have phi point and E phi linked by the product. So we'll be using the product rule. That means we'll have answer being a sum of two terms. So we're first going to begin by deriving the phi point. When you derive the phi point, it's going to give you phi 2 point. And notice again, you have phi 2 point because you are calculating the acceleration, second derivative. So phi 2 point suivant E phi. Then now you derive E phi with respect to time. It's like you have d de E phi dt. Even this, we looked at it. We are going to decompose the derivative. It's going to be d de E phi de phi fois de phi dt. So you have phi point coming out of it, and phi point times that phi point is going to give you phi point carré, and then d de E phi de phi is supposed to give you moins E rho. Okay, d de E phi de phi is supposed to give you moins E rho. It's like a rotation of 90 degrees. Remember that rule we looked at when you're deriving vector unitaire par rapport à un angle? It's like you are rotating 90 degrees. So E phi, you rotate it 90 degrees, is going to become minus E rho. That's why we have moins phi point carré E rho. That's why I emphasized at the beginning of the lesson that if you revised what we've done up until this point, these things are not going to confuse you because we are just using the same principles we were looking at in the polycopies. Okay, I think the only thing that's new here is the derivatives and all that stuff. But otherwise, all else is just the principles we have in the polycopy. So just revise the polycopy, make sure you understand it well, and these questions are going to be pieces of cake. So we come to the second term, here, omega point vectoriel M0M.
Mr. Charles,
Yes.
before you go very far, can you repeat on the derivative of this one, of Iffy, in the direction?
Derivative of Iffy par rapport au temps. When you look at the expression we have for Iffy in our notes, it's not written in terms of time, it's written in terms of phi. So we cannot derive it directly with respect to time because we do not have its expression in terms of time. So we are going to decompose it in a way in which we can derive it with respect to the variable it's been written in, okay, and still not change the meaning of the question. So what we normally do is we decompose the derivative. So if you have d de e phi dt, and you have e phi written in terms of phi and not in terms of t, we are going to say d de e phi de phi fois d de phi dt. That way the phi can cancel out there. It's like we are not changing the meaning. You have like d de e phi dt like that. Wait, just give me a sec. It's going to be equal to, we decompose it like this, d de e phi, then here you put the phi, because e phi has been written in terms of phi, multiplied by the phi dt. Okay, this way we haven't changed this because this defi and this defi can cancel out and we'll still have d de e phi dt. So it's like we haven't changed what's this side. Okay, yeah, so d de phi dt is going to give you phi point like that, phi point with a point on top there, and d de e phi de phi, this one, it's like you're going to rotate e phi 90 degrees. It's a principle in your polycopy. I've explained this several times. D de e phi de phi is like you're rotating e phi 90 degrees. And when you rotate e phi 90 degrees, e phi and e rho are orthogonal to each other. Okay, the meaning that 90 degrees to each other. So if you're going to rotate e phi 90 degrees, it's going to become e rho because e phi and e rho are 90 degrees to each other. So when you rotate e phi 90 degrees, it's going to become e rho. But it's just that the direction in which you're rotating it, it's in the opposite direction of e rho. So it's going to be moins e rho. And you have moins e rho there. And that's going to be your derivative for e phi. It's there in your notes. You'll find it there. This principle. It's nothing new. And that's our answer there. That's why we have phi point carré. It's because we are multiplying this phi point that's already existing there and this phi point that's come now. When you multiply them, you get phi point carré suivant e rho, like that. C'est clair?
Oui.
But you haven't written phi point.
Phi point is here. This one here.
Oh.
It's phi point carré. Phi point carré. There's a carré here. There's this square here.
Oh, okay.
You get?
Yeah, I get it.
Okay, great. It's clear for this first part of the vitesse d'entraînement. Okay, I guess it's clear. So we now calculate this term, omega point vectoriel M0M. We have the expression for M0M. It's this one here, A E phi moins A. Sorry, not E phi, but exponential phi moins A. Suivant E rho, we have it there. And omega, we said omega was equal to phi point. Now, since we have omega point, it's like we are deriving omega point with respect to time. So we're going to derive phi point with respect to time, and it's going to become phi 2 point. That's why it's become phi 2 point there, the omega point. Then when you are doing the product vectorial, the scalars, they do nothing. So you can just put them aside. When you're doing product vectorial, it's just between vectors. It's business for vectors. So scalars have no affair there. Just put them aside. It's not their business. So when you are doing product vectorial here, the phi 2 point is a scalar. We put it aside. It's got no business there. The A, we put it aside. It's got no business there. The E phi moins A, we also put it aside. They are all scalars. They have no business there. We're just going to deal with vectors. And the only vectors we have here are K and euro. So it's going to be K vectorial euro. And I explained this when I was giving you guys the rule for une base direct. We said that when they say it's a base direct, you write them as, let me just get the notation. You write them as euro there, and you write E phi there, and you write K like that. So, and then we put arrows like this. We put them there like that, and we put another arrow there like that. And just to show that they are vectors, we put a flash like that, like that. So when we say direct, it means euro vectorial E phi. When you're going in this clockwise direction, euro vectorial E phi should give you K. E phi vectorial K should give you euro. K vectorial euro should give you E phi. And when you start going in the opposite direction, they become negatives. That means euro vectorial K will give you moins E phi. K vectorial E phi will give you moins euro, ainsi de suite. So here you have K vectorial euro like this. K vectorial euro. K vectorial euro is going to give you what? E phi. And that's why we have E phi there. There's supposed to be a flash there like that. Okay, K vectorial euro, this one, K vectorial euro should give you E phi like that, this one here. And as I said, the scalars, you just put them aside. They have no business in the product vectorial. They're just wasting our time, you know. So it's going to be A phi 2 point, E phi moins A, E phi. The E phi coming from the product vectorial of K and euro. C'est clair?
Oui.
Okay, so I'm just going to remove that there. And next up, we now have the product vectorial double product vectorial. Same principle as we've done above. We have this one, this time here is not omega point, but it's just omega. And omega is phi point K vectorial A, E phi moins A, suivant euro from M0M, this term. So we can just get the scalars, we put them aside, phi point and A exponential de phi moins A. So we have K vectorial euro. As we found there, K vectorial euro is going to give us E phi. Okay, K vectorial euro will give us E phi. So now that we have E phi here, we are now going to calculate K vectorial E phi. K vectorial E phi. So K vectorial E phi is supposed to be moins euro. We made a mistake when copying here, but this is supposed to be moins. Okay, because from K to E phi, you're going in the opposite direction like that. So it will give you moins euro. And then you just get the constants. So constants, you have phi point and phi point. They'll be multiplying. It's going to give you phi point carré. You have an A there. So this is going to be A. And you have exponential phi moins A. And that's the exponential phi moins A there. Suivant euro, like that there. So that's going to be your double product vectorial. Is it clear for this one, for this term here?
Can you repeat it just once more?
Okay. So the scalars, we have no business with them. The scalars, we can just forget about them for now. Product vectorial, we deal with vectors. So in this first product vectorial that we have in the brackets, it's just going to be K vectoriel euro. And K vectoriel euro is going to give us EFI, comme on vient de le voir. K vectoriel euro is going to give us EFI. So now, what's going to follow next? We have EFI in the parenthesis there. Like this entire term is following EFI, like that. It's following EFI. Okay, so that means now we have phi point K vectoriel, the scalar that we have there following phi. So as usual, the scalars, we put them aside, we'll deal with vectors. So this time it's just going to be K vectoriel phi. And K vectoriel phi, remember I wrote euro there, I wrote K here, and I wrote phi like that. And I said, going in the clockwise direction, euro vectoriel phi will give you K, phi vectoriel K will give you euro. And when you're going in the opposite direction now, in the anti-clockwise direction, you get negatives. That means euro vectoriel K is going to give you minus phi. K vectoriel phi is going to give you minus euro, like that. And here, what do we have? We have K vectoriel phi. K vectoriel phi. It's K vectoriel phi. You notice the direction you're going in. It's in the anti-clockwise direction. So you'll get negative. So it's K vectoriel phi will give you minus euro. And that's why I put this minus here and the euro there. And what's just left now is to get the scalars and multiply them. The scalars don't do anything in the product vectorial. You just multiply them and forget. So you have phi point times phi point. It's going to give you phi point carré. And then you have A fois exponentielle de phi moins A, which is this one, A exponentielle de phi moins A. And this becomes your final term or final expression for the double product vectorial that we have here. Is that clear?
Yeah, it's clear. So it means we have to master a cycle here.
Yes, yes. By all means, you have to know it. This and the one in the spheric also. In the spheric, it's R. You have R. You have E, theta like that, and you have phi. In spheric, it goes like this: from E theta, phi, like that. This you have to know them. Okay.
Okay. Yeah.
Okay, then that means your gamma d'entraînement or accélération d'entraînement is just going to be the sum of these three terms that we found here. This one that we found, the second one we found there, and the third one there. You add them, you group like terms and all, and you get your gamma d'entraînement like that, which is this one there, after simplifying. I'm sure
I have a
it's clear.
question, Mr. Charles.
Yes.
Before you wrap that, yeah, you are
Okay,
proud.
just ask.
Okay, what is this? This.
What are you pointing at? Oh, okay, I've seen it. It's
Yes.
euro.
It's what?
Euro.
Then you told us to say if we multiply k produit vectoriel of k avec euro, that will be, is it not going to be in clockwise direction?
Yeah, so it's going to be phi.
It's going to be f in clockwise.
Yeah, K vectorial is going to give you phi. So in the brackets there, we'll get phi. But it's a double product vectorial, so we have to do it again. So this time we'll have K vectorial phi.
Oh, okay, I get it. Yeah.
Awesome. Then we go to the simplest of them all, the gamma Coriolis, acceleration Coriolis. The formula is just this here, it's just 2 omega vectoriel vitesse relative. The vitesse relatives are on a déjà calculé. The vitesse, oh sorry, this one is going to be angular vitesse, yes. Gamma, we have it as phi point k, So it says 2 phi point K vectoriel A phi point E phi, exponential phi suivant euro. As usual, the scalaire, we just forget about them for now. We deal with vectors and we have K vectoriel E rho. K vectoriel E rho. So from the cycle I drew here, K vectoriel E rho is giving you E phi. That's why we have E phi there. Then you just multiply the scalars. So it's going to be 2 multiplied by phi point carré times A times exponential de phi. That's how come we have 2A phi point squared exponential phi suivant E phi. And this becomes your gamma Coriolis. That's from this formula. So all you need to know is this formula, and just replace the expressions and you get your answer like that. That's gamma Coriolis. Are there any questions there? Okay, pas de questions. And then finally, you have been asked to calculate gamma absolu. So gamma absolu is simply la somme de gamma relative, gamma d'entraînement plus gamma Coriolis. We've already calculated all these three. So you just get gamma Coriolis there, plus gamma d'entraînement there, plus gamma relative. Gamma relative is this one there. You add them, you group like terms, and then you simplify the expression and you get your answer as that there. Okay, so we just got gamma relative is there, gamma d'entraînement is there, gamma Coriolis is there. Then you just get the like terms. Those following E rho, you group them together. Those following E phi, you put them together. And those following K, if at all there's any term following K, you put it there or you put them there. Then you simplify them, add, subtract, divide what needs to be done. Et voilà, vous aurez votre expression de l'accélération absolue qui est cette expression-là. There's also an alternative method. An alternative method, I don't know if it's longer or it's simpler. Je ne sais pas, ça dépend de vous. But when they ask you to calculate gamma absolu, instead of having to calculate gamma d'entraînement first, gamma Coriolis, then gamma relative, you just go directly, okay? You first derive, since you get your vector of position, since I want you to calculate gamma de M dans R, so you get your vector of position, puisqu'on est dans le repère R, our origin is 0, or it's O, so our vector of position is going to be starting from the origin up to the point we're dealing with. So it's going to be starting from the origin O, going to the point M. So we'll have OM par rapport à R, okay? So we'll be deriving OM par rapport à R first. So we're going to derive that one, do the OM de T dans R. We get our expression there, and then we derive it again, our second derivative, because acceleration is a second derivative. So you derive it again, okay? And still, dans R, you derive it par rapport au temps dans R still. But then you have to take note of the fact that you have an expression written in le repère relative R1, because you look at your expression there, you have euro, you have E phi, et tout ça. Those are the vecteurs de base dans le repère référentiel. Sorry, not referential, but repère relative, okay, and you're deriving now in the repère absolu. So you need to use formule de bord. It's there in your notes, formule de bord, for some of the expressions you'll be deriving there. So you derive it first, again you derive it, and you get your final answer. And what you discover is you get the same answer if you first pass through the stages of d'entraînement, the Coriolis, the relative, or when you just go directly, you still get the same answer. The problem with going directly is that you might get confused when it comes to formula de bord. If you don't know formula de bord very well, it might confuse you, okay? So you might get the answer wrong. But the good part about going through d'entraînement, Coriolis, relative is that the formulas have already been found for you. Okay, the deriving part has already been done for you. They've already come up with the formulas and all. So for you, you just have to substitute the values and you calculate a few things that need to be calculated and you get your answer. But if you're going to go directly, you just derive OM twice par rapport au temps, dans R, you will need to use formula de Bow, which might be maybe complicated for you. But when you reach, I don't know in which semester you guys will be doing solid. Those of you going to GGM, you will do it in S3. That's the first semester of your second year. You will now be working with Formula de Bow a lot because you will now be experienced in mechanics. So they'll suppose that you know Formula de Bow very well. So you won't work with vitesse d'entraînement, vitesse Coriolis, vitesse relative. No, you'll just be deriving. Every expression you're given, you derive using Formula de Bow and all that stuff. So that's that about exercise 4. I don't know if there are any questions in exercise 4. Est-ce qu'il y a des questions jusqu'ici avant d'entamer l'exercice 5? Est-ce qu'il y a des questions ou bien c'est clair? Are there any questions? Is it clear?
I have a question. Or can you simply give us like a simple summary when finding the vector of vector of acceleration of m that pair? So you were adding the sum of you were finding the sum of Coriolis, then relative, Coriolis, relative, and d'entraînement.
Yeah, the formula is here in the notes. The formula is here. Gamma, the m dans R, okay? Gamma absolute is equal to, you see they've even written gamma and the small a there to tell you that it's gamma absolute. The m is equal to gamma R plus gamma C plus gamma E, the m. And you have the formulas for all the terms. So acceleration de Coriolis, the formula is here. And acceleration d'entraînement, that formula I used is there. And acceleration relative, it's easy. You just derive the vitesse relative dans R1, and then you add them, and you get your gamma absolute.
So it's only when finding gamma absolute, that's when we take note of those vectors with my bar on top, with the directions only.
I don't get your question. Can you rephrase your question?
My question is, I remember last time we were finding this gamma of acceleration, this one. We were not forgetting about the constant things.
No, that's rotation. When you're doing rotation, when you're doing, no, not rotation, but produit vectorial. When you have a formula with a produit vectorial, you are just dealing with vectors. Produit vectorial. You get the name? Vector product, vector products. So you're just dealing with vectors. So the scalars, you just put them aside, you do your product vectorial, you get your answer, then you get your final expression. Only for terms with the product vectorial in them. Not the terms, but expressions. Only for expressions with the product vectorial in them. So if you have a formula that has product vectorial in it, like this formula, you do that. You have a formula like this one, product vectorial, you do that. This formula has no product vectorial in it, so there's no need for you to do that. And when we're doing the other exercise, we were doing coordinate freinet. In the coordinate freinet, the product vectorial does not intervene. So we were not doing that because that formula doesn't have product vectorial in it. Okay, so when you have product vectorial, you do what's required of the product vectorial.
Okay.
Yeah. Are there any other questions concerning exercise 4? Okay, I'm guessing it's clear. We go to exercise 5. This one will try to be fast because we have to finish this today. So our exercise reads, this one is a bit complicated. I don't know if an hour will be enough, but follow me properly. That's why I asked if you guys revised what we did last week. Yeah, and if you revised your notes, because for this one, this question here, you need to know your notes very well for you to understand it properly. This is like a good exam question, you know, the part of the exam that has to do with cinematic. This question it's a good one. So follow me properly. Soit un cercle de centre 0, 1. So we have this circle here, circle, and I said the center of the circle is 0, 1. So meaning the center there is O1, et the rayon A. So the radius of the circle is A, like that. Soudé à une tige. So soudé means it's welded or it's connected to a tige. A tige is this line there. A tige is just like a pipe or a cylinder or something. But this one here, it's a tige. Delta, so the tige, we call it delta. The longer L, so the length of the tige there is L. L'ensemble formé par la tige et le cercle tourne dans le plan OX, Y, Z. So take note of this also. They're telling you that this entire thing here, this entire thing, it's looking like a lollipop. It's turning dans le plan OX, Y. In this plan, this thing is turning, meaning it's going like that. It's turning in this plan OX, Y, like that. Du référentiel absolu R, O, I, J, K. So take note of this also. Référentiel absolu. You have to identify le référentiel absolu, référentiel relative et tout ça. So you have a référentiel absolu, which is R, O, I, J, K, avec une vitesse angulaire constante, oméga. Again, take note of this. This is how you decompose questions in mechanics. All these things are very important. Make sure you understand your question very well. So when they tell you une vitesse angulaire constante, so take note of this. Your vitesse angulaire is constant because we'll be deriving a lot. So you need to know what's constant, what's varying, what's mobile, what's fixed, and all that stuff. So we've been told our vitesse angulaire is constant or not. And we have R1, O1, U, V, K lié à la tige. À la tige est le référentiel relatif dans son mouvement. La tige est repérée par l'angle phi. So, the tige est repérée par l'angle phi égale à I. When they say phi equal to, and they write two vectors like that, it means this angle phi is between these two vectors. So you have I and you have your U as this one here. It's not labeled. The woman forgot to label the diagram in the question. Sorry, give me a second. Okay, we continue. So phi is the angle between E and U. So U is this vector there, this vector going in that direction like that. So phi is between E is there, and U is there. So this angle there is the phi. Une particule M se déplace sur le cercle C. So the the particle M is found on the circle. As you can see, this M is there, it's on the circle. So it's moving on the circle like that. Elle est repérée par l'angle θ égale UOAM. So theta is the angle there. Theta is between U and OR. OR is there and M is there. So this angle there. So as M is moving like that, it's moving with an angle theta there. And they tell you soit euro, E phi, K, une base mobile liée à la particule M. Soit euro, E theta, K, une base mobile liée à la particule M. So to this particle M, you have euro like that, you have E theta there, and you have K, l'axe vertical. It's not represented here because we are in a two-dimensional figure like that. So as M is moving on the circle there, even this base is moving with it. That's why they are saying une base mobile liée à la particule M. So as M is moving there, even these guys are moving with M and they are changing direction depending on the position of M on the circle. So, they've then given you a condition. Les résultats doivent être exprimés dans la base euro, E theta, K. Because here you have three bases. You have EJK, you have UVK, and you have euro, E theta, K. Okay, so you might get expressions following EG, you might get expressions following UV, you also might get expressions following euro, E theta, K. But the final expressions all have to be written in euro, E theta, K. All of them, all your final answers, they have to be expressed in this base. So now we go to the questions. So that's how you interpret the figure. It's another important aspect of mechanics, how to interpret these diagrams, because almost all the questions you get in mechanics have a diagram to them. So you have to be able to interpret the diagram, so it also helps you in your imagination and all. Calculer le vecteur vitesse et accélération relative de M. So this time we're beginning with the accélération et le vitesse relative. Vitesse relative, c'est la vitesse du point M dans le repère relative. And what they've told us here is that R1 avec à l'origine O1 UVK lié à la tige et le référentiel relative. Okay? So, what's the vector position we're going to use in this question for us to calculate the vitesse? Because vitesse is going to be the derivative of the vector position par rapport au temps. So what's our vector position going to be? What's the origin we use? It's an open question. Hello, are you guys there? Total silence. You guys can hear me, right?
Yes, yes.
Ask the question, say, what's our vector position going to be? For us to calculate vitesse, vector vitesse relative de M, what vector position are we going to use? Is it going to be Zm? Is it going to be Vk? Is it going to be Fj? Is it going to be Do? Is it going to be, what's it going to be? According to the question we have there, according to the question, the énoncé, and also the figure, what's our vector position going to be for us to calculate la vitesse relative de point M?
Okay, can I try?
Yeah, yes, go ahead.
Yeah, but I don't know really it, but connecting to the last question you gave us, you used R1, so which was a position above, not really the the ZY we were using, but I don't know how to say where it is there on top.
Okay, okay. Anyone else to give it a go? Thank you very much, Ruben, for trying. That's what's important, at least. You try for essay. Anyone else to give it a go? Try. Come on, guys. We just did 2 exercises. Actually, we've done 1 exercise with changement de référentiel. An exercise where we've calculated vitesse relative several times. I explained it last week. I explained it today. And you guys still don't know the vector position you use when calculating your vitesse relative. First of all, do you even know what a vector position is? What's a vector position? What does it do? Why do we have to know, or why do we try to establish or find the expression for the vector position? Why do it in the first place? That's from the name itself, vector position. What's the purpose of the vector position?
I think to find the position of it,
The position of what?
of the point M, which is not like in the common repair Z in X, Y, but somehow complex.
The answer you got it the first time is just for us to know the position of M in the repair we are working in. That's why we get the vector position. It's just to know the position of M. Okay? So, in our repair relative, in this case, we have a question is telling us R1 is le référentiel relative. That's our repair relative. R1, O1, UVK. Okay? We know the origin there, and we can now get our vector position from there. So from the repair R1, what's going to be our vector position? What's going to tell us where M is located? What are we going to use? Is it OM? Is it LM? Is it XM? Is it YM? Is it what? What we're trying to get from the origin to the point M. From the origin to the point M, it's going to be our vector position. For us to know the position of M in space, it's just the distance or the movement to the position of M from the origin. So what's going to be our vector position? It's going to be what? In the repair relative that we have here, repair relative, what's going to be our vector position?
To be easy.
What's going to tell us the position of M? And that's moving from the origin to the point M. Just from the origin to the point M. So what's going to be our vector position? All you just need to do is to identify the origin of our repair relative in this case. What's the origin of our repair relative?
O1.
O1, yes. O1 is the origin of our repair relative. So what's going to be our vector position? We'll be moving from the origin to the point M. From the origin to the point M. So the vector is going to be
UVK.
the vector from the origin to the point M is going to be what? Guys, estamos levering. Hein? We are not revising. Et là, il y a un grand problème. Because when we were looking at le coordonnées, that's the first thing we're beginning with. Vector position, vector position, vector position. Now, if you cannot identify your vector position, how are you going to calculate your vitesse? How are you going to calculate your acceleration? How? It's impossible, c'est impossible. Because the vector position is the first step, it's the beginning. So if you cannot begin, you cannot advance, you cannot go anywhere. Okay, we looked at this vector position. That's the first thing we were trying to find, the position of M in the repair we're dealing with. How we're going to get to M. Hey, this one. Vector position. The vector position here is what? What's this term here on my left-hand side?
OM.
OM. That's your vector position from the origin to the point M. Because as you defined it yourselves, vector position is telling you the position of M in space or in the repair you are dealing with, the position of M. So you are moving from the origin of that repair to the point M. So a vector position is simply OM, but not always OM. We're just saying OM here because the origin of our repair is O. Even here in the coordinate cylindric, vector position, it's even written here, vector position, the M on coordinate cylindric, OM, we have it there. When you go to spheric, you'll find the same thing. That's the first thing we are looking at in all of them. The vector position, OM there. OM is equal to R, ER. Because that's what's going to give you the vitesse. You'll be deriving the vector position. Acceleration, you'll be deriving twice the vector position. So when we go back to our question here, come to our question there. Dans le repère relatif, what's going to be our vector position? I ask you guys again. Knowing that this guy here, let me highlight it. I'll put it in a box. This one here. That's your repère relative. Okay? That's your repère relative. And we want the vector position the M. Vector position the M. What's going to be a vector position the M this time? What's the origin of this repair, this referential? What's the origin?
It's O1.
O1. So we're moving from O1 to M. So our vector position is going to be what? O1M, not so.
Yes.
Tout simplement, O1M. That's going to be a vector position. So now what you just need to find out or to work out is the value of O1M. That's it. If you cannot identify the vector position, you cannot advance. That's the first step in any exam you'll be doing, in any exercise you'll be doing, for you to calculate the vitesse, for you to calculate acceleration, for you to go on and calculate the force and the potential energy and kinetic energy and everything else you'll be doing in Mécanique du point, you will first begin with the vector position. That's like the most basic thing you have to do. So vector position is simply the distance or the position of M from the origin. So when we say find the vitesse relative, we're just asking you to derive the vector position. So here we'll just be deriving ORM. That's it, ORM. We derive it in R1 because that's our repère relative. When we're working with vitesse relative, acceleration relative, we are working dans le repère relative, tout simplement. So you guys are not revising. You're not revising mechanics. Every week we have these same problems. Okay? Every week you guys are behind. You guys are failing to answer questions from the polycopy, things that I spent so much time explaining. You have videos on YouTube, you have the polycopy with you. You just go through 2-3 times. You understand the stuff. But every time we come here, it's like you guys don't know what's happening. You're failing to answer simple questions, and it shows that you are not revising mechanics. Okay, you are not revising. And all this time, this is time. Okay. Now I doubt we'll even be able to finish this exercise today because I'm sure a lot of things are going to confuse you down the side. And this question is a bit complicated. So if you don't know your notes well, it's going to confuse you. So we begin, and here we have our repère absolu. It's been identified as ROIGK, and we have our repère relative à la tige, ROUVK, like that. And then we have our omega, or yes, omega is omega k equal to phi point k, like that, because this is rotating there like that. And they're asking you to calculate vitesse relative du point M. There's supposed to be a flash here. I'm sorry, I forgot to write it because I told you I used to copy these things fast in class, so I used to make a lot of mistakes. I hadn't understood mechanics very well at the time, so I didn't know the importance of the arrows and all that stuff. So there's supposed to be a flash there. You guys, as people that understand mechanics well, should know better. And the relative du point M is going to be equal to la dérivée de ORM, as I'm from telling you, the vector position OR of this repère relative, because OR is the origin of the repère relative. As you can see, OR is the origin of the repère relative. So we're going from OR to le point M, like that. And what's this distance here? Now this one, you don't even have to be a good mechanist. You just need to understand the question well. Okay, from the question, we're moving from OR, the center, to the circumference. From the center to the circumference. What's this distance called generally in circles? The distance from the center to the circumference.
Radius.
The radius. And from the question, we were told that the radius is equal to what?
A.
A, exactly. So that means the distance between OR and M is equal to what?
Is equal to A.
Is equal to A, simply. And we have the vector, the direction, so dans quelle direction? So euro here. So that means ORM is simply A dans la direction de euro, tout simplement. And it's even good because we've been told to express all our answers in euro, e theta, and k. So now we have our vector position ORM écrit dans la base euro, e theta, k, which is good. So we have OM being equal to A, euro. So this is another trick you're supposed to know when it comes to circles, because you will be forced to find the values of certain vectors, like vector position and all that stuff. So if it's on the circumference of a circle, just get the radius, just try to find the radius and you have your distance there. These are les astuces. In French, they call them les astuces. They are tricks, techniques. So as you solve more mechanics questions, as you go to school, you do more TDs with your teacher, you get more tricks and more techniques to solve mechanics questions. Just take note of all of them and try and use them. So here's this one. When it comes to circles, the radius is also very important. So it's important for you to take note of the value of the radius and all that stuff. So we have our DORM dt being equal to A suivant E rho. Okay, A suivant E rho. So now we're going to derive this. Okay. Now, there's a bit, I said this question is a bit complicated because it's different from the first question we had. In the first question, exercise 4, we only had two repères. We had the repère absolu and the repère fixe. Here we have three. We have le repère absolu, the repère relative, and we also have this one here. This is just the repère mobile. So that means this repère mobile here that we're working in, because we have euro belongs to this repère mobile there. even when we are in the repère relative, it's still going to be mobile. Because in exercise 4, if you guys remember very well, we said when we are deriving euro, phi dans le repère relative, they are going to be fixed. But in this question, they are not fixed, okay? Because our repère relative is different from these guys there. These guys are out of the repère relative. So that means even from the perspective or from the angle or from the view of the repère relative, euro, e theta, and k, not k, sorry, euro and e theta are moving, they are mobile, like that. So when we are deriving this, even though we're deriving it in R1, euro is still going to be mobile, okay? Because euro is there, it's moving with a point M, and le repère relative is this one here, UV. So that means when you stand in UV and you look at this repère, euro, e theta, it's still going to be moving, still going to be mobile. And that's where mechanics really calls for your imagination. You try to imagine these things, you try to see them, try to say, okay, so if I'm in this repère, is the other one going to be moving? Okay, I'm in this repère, is it moving? I'm in this repère, is this repère moving with respect to itself? And you ask yourselves those questions and you're able to answer them. So euro, e theta, they are moving even in the repère relative. So we are going to derive this euro because the R is fixed. It's just the radius. The radius is not changing. Euro is what we are going to derive. And when we derive euro par rapport au temps, it's still going to be the same rule we had. We said de euro dt is equal to de euro d theta. This time we're working with, I know in the polycopy you have phi, but they've just replaced phi with theta. It's the same thing, it's just that they've just changed the angle there. It's just to confuse you guys a bit, but it's still the same principles. It's just the angle that they've changed. It's just like notation that's changed, the notation that's changed, but same principles. So the theta dt, like that. So the theta dt is going to give us theta point there, like that. And the rho de theta is going to give us e theta, like that. And as I've said, I repeat, in the polycopy you have phi. So it's de euro de phi fois de phi dt. And it's going to give you e phi fois phi point. But there where there's phi, they've just put a theta. But the principle is still the same. So instead of working with a phi, you just work with theta this time. So your final answer is going to be e theta fois theta point. And that's why we have theta point e theta. It's this guy here. Theta point e theta. They are coming from there. So we have theta point e theta fois le 1 there. And that becomes your vitesse relative, like that. Is it clear for the vitesse relative? Huh?
In the question, was it indicated the theta?
Yeah, theta. Let me just let me remove these things. The theta was indicated. It's the angle between U and ORM. When you go to the question, they told us theta is this one here. It's the angle in the circle, this one here, between U. The theta is the angle between U and ORM. So theta there, and like that there. Between
okay.
and that, it's the theta there.
Yes, I see.
So when you work them out, you find that this theta here is also being found in this euro and e theta. When you just work out the angles using angle properties and all that stuff, you find that this theta is intervening even here also. That's why we have the right to use the theta there.
So when we are given the theta, then we should forget about the phi.
The phi. Yeah, it's all about interpretation of the diagram you've been given. They won't give you exactly what's in your polycopy, huh? Because in the polycopy, you have euro being written in terms of phi, and in the exam, they'll give you the same thing. They might change the angle. So maybe they won't choose theta, they won't choose phi. They will use maybe x to represent the angle. They just tell you x is the angle there, there, and there, okay? And then they even give you ex and euro. So now you just have to interpret the figure yourself, the diagram, say, okay, this is representing that. So since euro and ex are at 90 degrees to each other, so when I derive euro par rapport à l'angle x, I'll be moving from euro into ex like that. It's all about interpretation of the figure. Because here you see the phi has been given as the angle down this side. So if you just use phi, it's like you would have confused everything already, because phi is the angle here, the rotation of this entire thing with this side. It's not anywhere with these repairs, these two repairs, euro, theta, and UVK. No. So you just interpret the figure yourself. You say the theta there. It's like the angle also coming this side, like that. It's like you get this U, huh? You get this U. When you translate it there, you put it there, like that. It's going to be the angle there, like that, on top there. Let me demonstrate this U. If you bring it there like this, so theta is going to be this angle here, and this is a theta there, like that. A theta, sorry, euro, like that. So theta is the angle there. We can label this as theta, like that. And then you have your vector theta there at 90 degrees with this. Okay, so if you want, you can bring this side there like that. The U, you can still translate it there, like just continue translating it, or not even translating the U, because this theta is there, the angle theta is making there. So it's like euro, as it's moving like that, it's moving with this angle theta here, as you can see, euro in its movement like that. If it starts moving like that, it's moving with this angle theta that's here. Let me remove this. Yeah. Sorry. Yeah, so the angle theta there, this angle theta is the angle here. So euro, as it is moving, it's moving with this angle theta. So that means if I rotate a theta 90 degrees with this angle theta, or if I rotate 90 degrees like that, it's going to rotate into a theta. And that's where I use that rule there for euro de theta, giving you what? A theta. Because if I rotate this euro 90 degrees like that, if I rotate it into this one there, it's going to rotate into this one, the E theta, if I rotate 90 degrees. Because the rule is that deriving a vector unitaire par rapport à un angle, it's going to give you, it's like rotating it 90 degrees. So when you rotate it 90 degrees, it's going to rotate into its the other component in the bus, because all these guys are at 90 degrees to each other, as I have already explained. So E theta, so E rho, E theta, and K, they are at 90 degrees to each other. So if I rotate this E rho 90 degrees with par rapport à this angle theta, like if I move it 90 degrees, it's going to move into E theta. And that's why the formula, this formula here, de rho dt being equal to de rho de theta, like that. De theta fois de theta dt. So this component here, we say it's like we are rotating this vector euro by 90 degrees. So if I rotate this euro by 90 degrees like that, it's going to rotate into this E theta there. And that's why it's going to be, the answer there is going to be E theta, like that. It's just because of this angle theta is one that's working in this case. In the polycopy, this angle is phi. In the polycopy, this angle is phi. But in this question, the angle is now theta. That's why we have our theta there. It's just to test you guys, to test your understanding of the cool and all that stuff, to see if you get confused. Is it clear, Danny?
Yes, it is clear.
Okay. So this is going to be our Vitesse relative. Then we calculate our Vitesse, gamma relative now. Gamma relative will just be deriving Vitesse relative, and still we're deriving it in R1. So we have our Vitesse relative as this expression here, A theta point E theta. So we're going to derive this again. Theta point is varying, E theta is still varying. So we are going to derive theta point. We'll have A theta 2 point E theta minus, we are going to derive E theta again. It's going to be de E theta égale de E theta de theta égale d de E theta sur d theta. As usual, we decompose it, multiply it by d theta, d theta d t. This one is going to give you theta point, and then this one is going to give you minus E rho, like that. That's the same principle you have in your polycopy, except it's phi. In the polycopy, it's phi, but this time you just put angle theta, and we continue. So when you derive a theta, it's going to give you this. So this theta point multiplied by this theta point that's already there, you get theta point carré. Then you have suivant euro, and then you have minus there, which is this minus here, and you get your final answer as that. So it's going to be A outside minus theta point carré suivant euro plus theta 2 point suivant E theta, comme ça, as your gamma relative. Very simple to calculate. The moment you identify your repère relative and you find out your vector position and its value, the rest from there is simple stuff, because you just be deriving. So you just derive and you get your expression like that. So is it clear for these two, the Vitesse relative and gamma relative? Is it clear?
Yes, it is clear.
Okay, so we now go to vitesse d'entraînement. Same formula, the same formula we had in the other question is the formula we'll be using even here. Okay, the same formula. So we said vitesse d'entraînement is going to be equal to vitesse of the origin of the repère relative. The origin of the repère relative we said is what? O1 par rapport à not par, yeah, c'est par rapport à R. We said par rapport à R, ou dans le repère R, le repère absolu. This is the formula. Plus rotation de R1 par rapport à R0 vectoriel OA M. That's your formula for the vitesse d'entraînement. You have the formula in your books. So this one, vitesse de OA dans R, because we are in R and we are calculating the vitesse of the point OA, we are going to use the vector position. The origin of the repère we're working in is 0, and the point we are working with is OA. So the vector position is going to be OA. You see why it's important to know vector position? Because this term, I'm telling you, this term particularly confuses a lot of people. This term here, this one here. Sorry. Let me highlight it. This one here. It confuses a lot of people, huh? This one. Because when you say vitesse de OA par rapport à R, you don't know what vector position you're going to use. So people end up using the wrong vector position. But for you, you know that if I'm doing vitesse de OA, the point I'm trying to get to is OA, and I'm working in R, so I need to get the vector position of OA in R. That means I'll be moving from the origin in R to the point OA. Okay, so the origin of le repère R is O, and so I'm going to move from the origin O, the point, the origin of the vector of the repère relative. So our vector position is going to be OA. Make sure you learn this trick, guys. I emphasize. Make sure you learn. You know how to get your vector position. That's your beginning. If you cannot get it right depuis le commencement, tout ce que tu vas faire sera incorrect, malheureusement. So we get delta OA dt, we're deriving it in R, as you can see from the formula. This is an established formula. It's always in the repère absolu. And then we have our rotation there. We have our omega k vectoriel, OAM. It's going to be, we already got this vector here. It's this one here. It's A suivant euro, comme ça. Then we need to get the value of OA. So we come to our figure here. We have O, or moving from O to OA. O to OA. I would like one of you to just try to tell me the value of this distance here, to see if you guys are imagining from O to OA. O to OA. Just try. You have your OR there, like that. So we want the distance from here to there. Not the vector, don't include the vector. Just tell me the distance. Who can try? Just looking at your figure. Because this is important. In the exam, they won't tell you that OOR is equal to this and this. It will be up to you to interpret the figure yourself. Okay? So just try. You know, this is how you learn. You try today, you get it wrong, you won't forget from there. Or you try today, you get it right, and you're impressed by your efforts, and you are even motivated to try more next time. So just try. Anyone, the value of the distance OOR, not the vector OOR, but just OOR, the distance from there to there is equal to what? From here to here. Just look at your figure well. Ruben, Lawrence, Danny, 116, and Etoile. 316 guys, ka?
Yeah.
Yeah, so just try the value of OOR. If I can give you a clue, you already have your L there. You already have something that you know this side.
First, where is L engine?
Just here on the circle.
Then it will be adding this L to that radius you gave us inside.
So the answer is going to be
L plus A.
exactly. Chapwa, L plus A. That's your distance, OOR. It's L plus A. Just like that. This is how people get marks in mechanics. Huh? Just these small things. Because even here, you can lose marks if you just fail to interpret OOR. Washala. So, as you guys have said, OOR is simply L, because from 0 to this part here where the circle is beginning is L. As they've told us that the tige, the longer L, so the tige is going from 0 to this point here, the tige, and it's L. Then from this point to O, we know that it's from the circumference to the radius, so it's A, as you guys have said. C'est très bien. I'm impressed. Or following. So, as you can see, OOR is just L plus A, and it's following which vector? It's in U. And I know the question is saying express them in rho, theta, and k, but you can express that at the end after you derive, okay? It's going to be much easier like that, because here it's easy for you. If you already convert it, you'll be doing more work. So we'll just work with U in the time being, okay? Because OOR is in the direction of U there, like that. So we'll just work with U in the meantime. And when we get the final answer, we can do the projections and convert U to euro, theta, and k. So whatever the expression is going to be. Then from here, we have this other side where we're doing the product vectoriel. As usual, with the scalars, we put them out. It's going to be R omega there. And then K vectoriel euro. K vectoriel euro is going to give us E theta. So this here is not supposed to be there, the plus. That's supposed to be A omega E theta. A omega E theta as the product vectoriel. This side is easy. I'm sure you guys have noticed with the product vectoriel and stuff. If you just know that cycle that I gave you, it's easy. Here is where we need to do some work. So as usual, when you look at this, you see this U as it's rotating with this angle phi. You see this car? U, because U is this there. U is a vector unitaire for in this direction. So U is rotating with this angle phi. Okay, so that means the expression for U, even though we don't know it, it must be in terms of phi somewhere. So when deriving U, because we have the U, the T there, what we are going to do is this. We'll say d de U d de U dt is going to be equal to d de U, not forgetting that this is a vector like that, over which angle? As you have seen, the angle is phi, it's making, yeah? As it's rotating with an angle phi, multiplied by, as usual, d de phi d t. We have not changed anything on this side of the equation. Still the same as what's this side, because this d phi and this d phi can cancel out. So bien sûr, d de phi dt is going to give us phi point. And when deriving this one here, we are still using the principle of deriving a vector unitaire par rapport à un angle. So normally the figure is like this, okay? You have a vector like that, and we call this U, but the base is U V K. So this is going to be V, okay? And this side will have minus U, okay? And then the angle between U and V is what? 90 degrees, n'est-ce pas? It's 90 degrees. And even this side is 90 degrees. And we have been told that whenever we are deriving a vector unitaire par rapport à cet angle, because we know U is like this. We go through there, we go through in that direction, and then we have this angle phi there. And we know that E is rotating in this direction like that, or even in this other direction, but it's rotating like that. Okay, so if we're deriving U by this same angle phi, it's like we are rotating U 90 degrees. Okay, so if I rotate U 90 degrees, like I'll be moving it from here to there, it's going to become V. Okay, so when we're told to derive U par rapport à cet angle phi, it's like we're being told to say rotate U 90 degrees. That's the general rule. This rule, you guys have to know it. Okay, when I tell you to derive U par rapport à cet angle phi that it's making when it's moving, it's like I'm telling you, rotate the U 90 degrees. So if I rotate this U 90 degrees, it's going to become what? V. So that means the derivative of U par rapport à cet angle phi is going to become what? V, like that. It's the same principle we used for euro and E phi when we derived euro par rapport à phi and it gave us E phi. It's the same principle we used in the first question when we derived euro par rapport à theta and it gave us E theta. Okay, it's just application now. They're just changing the angles and the vectors being used. As I told you, they'll just give you something like this to just confuse you, but it's the same principle you're using. So if you've understood that principle, that if you're deriving a vector unitaire by an angle, the angle that it's making with when it's rotating, it's like they're asking you to say rotate that angle 90 degrees. So you know that okay, so if I rotate it from if I'm deriving U par rapport à phi, I'm being asked to derive it. Oh, sorry, I'm being asked to rotate it 90 degrees. And because U is orthogonal to V, that means when I rotate U 90 degrees, it's going to become V. So is it clear? Is it clear, guys?
Shows. The question is, so if we have been following well the cool, so it's like they have just changed, they have just replaced here V can also stand for EZ, not so.
No, not EZ, but FE. If you're looking at the coup.
FE.
Yeah, FE, yeah.
Ah.
And then U is like euro. So if you go to that part in the coup, this part, let's just give me a sec. If you go to this part in the coup, where's that part? It's here. Dérivé d'un vecteur unitaire par rapport à un angle phi. You see, you have euro, you have e phi. So when we tell you to derive d de euro par rapport à d phi, it's like we're asking to derive to rotate euro 90 degrees. So it's going to become that. That's why we had d de euro, it gave us here, d de euro gave us e phi. So this part of the coup, we're just applying it. So here where we have euro, there's U. Here we have e phi, there's V. With the angle is still phi.
Yeah, it's clear. It's clear.
Okay. So it's just application of the code. This is why I'm emphasizing it. Guys, no matter guys, mamonaka. So when you derive U, here U dt, as you will see on the next page, it's going to give them phi point V, like I was from writing there, phi point V, and that's your derivative there, okay? And then now what you need to do is to convert this V into, to change it, because the question is, it has specified, les résultats doivent être exprimés dans la base euro θ k. So you can't get an answer following V, because it's not in this base. So that V, we need to do something about it. Okay, so you come to your figure here. You have E theta, you have euro. This, let me retrace it here. Imagination. So you have like that. This is your euro, and this is your E theta, like that. Like that. These are on the circumference of a circle there. And then in the circle, we have something written like this. Yeah, like that. This is U and this is V. So this guy, you can translate it. When you translate it here, it's going to come something, it's going to appear something like this. You have that there and you have that there. Okay? So this is going to be your V and this is going to be your U. What I've just done is I've just moved this and I've moved it here. I've projected it to there and it's become something like that. So if I can just erase this and come back up here, I have E theta euro. So if I just move this, I move it to this part here, I'll have the V being there. I'll have the V coming there like that. This is going to be V. I've just translated this vector, I've projected it up here, and this U, just still parallel like that. I move it there, it's going to be there. And I know that the angle ORM or euro is forming with U is theta. That means the angle here is going to be theta. And if you know properties of angles, even this angle this side is going to be theta, this angle here. If you work it out, you can try it. If you work out this angle there, it's going to be theta. That's where the woman got this figure from. This figure you have here. So you guys can see this figure here. You have theta, euro, and you have V, and you have U, like that. And this is also something else you need to know. As I told you, as you are doing TDs, don't focus on the results you're getting, the final answers. Focus on how they are solving the questions, the tricks and techniques they're using, because those are the things you will be working with. So even this thing, how to translate a whole plane into another plane so that you can resolve one vector in terms of two other vectors, you need to learn how to do it. So you just imagine this V, you just bring it up here. It's going to be like this. These two are parallel, and this U, you bring it like that, and you get this figure down here. Okay. Then from here, now you form right angle triangles. As I told you, right angle triangles are golden in trigonometry and mechanics. E theta and E rho are what? They are orthogonal to each other. So they are 90 degrees to each other. So this E theta, I can translate it up here like this. I can translate it there like that. And it's going to be like this. E theta going there and there. And because E theta and E rho are meeting each other at 90 degrees, this angle here also is going to be 90 degrees because it's still E theta and E rho, it's E theta and E rho. So now I have this right angle triangle with my hypotenuse being V there, and this there, and that there. And because I'm dealing with base vectors or a vector unitaire, this side, I can just take it as, but wait first, let me just, this theta here, the theta here, excuse me, we said this angle here is theta, this angle here is theta. When you work it out, you find that this angle here is theta. So that means E theta and V are forming an angle theta. So this E theta here that I've projected and this V down here, they will form an angle theta, like that. And I'll be dealing with theta now. So this side here, the E rho, is going to be the opposite of this angle theta. So it's just going to be sine theta. And this angle, this side here, the E theta, because it's adjacent to this angle theta, is going to be cos theta. And because I'm dealing with vectors now, I'll be moving from this point to that point there, like that. Don't choose SOHCAHTOA here when you're dealing with vectors. When you're dealing with vectors, it's like you're looking for a way to get from this point to that point. So instead of going this way to that way, which we're looking for, we can go this way and then that way. So if we go this way, it's going to be sine theta suivant E rho plus cos theta suivant quoi? Suivant E theta. That's why we have sine theta suivant E rho plus cos theta suivant E theta. Now, you might ask, why is it just sine theta here? As a way to remember it, you can just say, when you're dealing with base vectors like E theta, E rho, V, and U, when the side is opposite to the angle, you just write sine theta without anything else, just sine theta. And when it's adjacent, you just write cos theta. But what gives you the right to use that? Okay, what gives you the right to use that? It's because it's on the vector unitaire. Remember last time we had this side being equal to rho, yeah? We had this side being equal to rho. Okay, when you look at this figure that I gave you some in one of these, yeah, here we had this side. No, not in the spheric, cylindric. Yeah. Here, when I got this, my hypotenuse was rho, so the x side became rho cos phi, because it was adjacent to it, and the y side, it was opposite, was rho sine phi. Okay, so rho is simply the magnitude of this hypotenuse, the magnitude of this hypotenuse. Now, when you come to our solutions here, the hypotenuse here is the vector v. What's the magnitude of the vector v? V, c'est a base vecteur, ok? Ça appartient à une base, parce qu'on a une base, UVK. So that means U, c'est un vecteur unitaire, V, c'est un vecteur unitaire, et K, c'est un vecteur unitaire aussi. And when you have a unit vector, its modulus is equal to what? When you have a unit vector, its modulus is equal to 1. So the modulus here is 1. That means wherever there's a rho, we'll put 1 this time around. So here, because we had a rho sine theta, so where there's rho, I put 1. and I had a rho cos theta here. So where there's rho, I put 1. So I'll just be left with sine theta and cos theta because I'm dealing with a base vector here, the V. It's a base vector. That's why you just go direct and write sine theta cos theta because it's a base vector. Its modulus is equal to 1. So V is going to be equal to sine theta rho plus cos theta e theta. And where there's V there, you just replace with that. That means you would have successfully expressed V in terms of e theta and e rho, and you'll get your final answer for vitesse d'entraînement as that there after you simplify this expression there. Est-ce que c'est clair?
I want to know how you got the angle E theta V as theta.
Yeah, it's just 90 degrees. It's just imagine 90 degrees, okay? 90 degrees. I'll show you how. So V and U, they belong to the same bars, so they are 90 degrees to each other, not so. That means this angle here is going to be 90 minus theta. You agree, not so?
Oui.
And then E theta and E rho are at 90 degrees to each other, not so? Because they belong to the same bars. E theta and E rho, they're at 90 degrees to each other. That means this angle is 90 degrees. E theta and E rho. Let me change the color. Format.
Oui.
I'll use purple. Here. This is 90 degrees also. Okay? So if it's 90 degrees and this angle here is 90 minus theta, for this to be 90, this angle here is going to be what?
Theta.
It's going to be 90 minus theta, which is just going to be theta.
Theta.
Yeah, it's just working out angles, 90 degrees and all that stuff. As I told you guys, right angles, 90 degrees, they make work very easy for you. So it's easy for you to work out angles, it's easy for you to work out triangles and trigonometry and all that stuff. So you get why the angle between A theta and V is theta, huh?
Yeah.
Are there any other questions?
No.
Okay, so it's already 14, but I'll try and go quick so that we just finish up this part. Because the rest of the part, we're just applying formulas, yeah? You have the acceleration Coriolis, you have the formula for acceleration Coriolis, you have what we're going to start calculating next, gamma d'entraînement. You just use the same formula for gamma d'entraînement that we were using in the first question. You first calculate gamma of OA dans R plus this one, this term, d de omega. D de omega, if you look at this part here where we're calculating d de omega, is equal to 0. Do you remember why d de omega will be 0? Okay, so it's understandable that you would have forgotten.
What's the question?
These are why d de omega is equal to 0. D de omega dt. Yeah, and as I said, it's understandable that you guys don't know why, because they're not details that you pay attention to just yet. But from now on, you pay attention to such details also. They've told you avec une vitesse angulaire constante. Vitesse angulaire is omega, and omega is constant. So meaning its derivé par rapport au temps is going to be equal to 0, because it's not changing in time, it's constant. It's moving at a constant speed, at a constant velocity. So when you derive that velocity to get the acceleration, you find acceleration is 0. It's not accelerating because the velocity is not changing. So such details, you pay attention to them also. They simplify your work, because if you say vitesse angulaire, maybe you've forgotten that the vitesse angulaire is constant, you derive it there and you find a term that's not supposed to be there, and it's going to confuse your answer. So when you tell you vitesse angulaire constant, d de omega dt is going to be equal to 0. You guys get, huh?
Oui.
Yeah. So they told us vitesse angulaire constant. So d the omega, which is the vitesse angulaire constant, d the omega dt is going to be equal to 0. So that means this term, we can even cancel it out. This term, there's no need to calculate it because this is 0 and 0 vectorial, any vector inside is going to give us 0. So we just need to calculate this guy and this guy there. Then this gamma de OR dans R is just going to be the derivative of V de OR dans R, which we already calculated. It was this guy here, this one here. It was this one here, L plus A phi point suivant V. That was V de OR dans R, which is this one here. So when we derive this, L plus R is a constant. So we'll just be deriving phi point and V. The derivative of V is still going to be the same principle we did for you. It's going to be dV dt equal to dV. The angle we're working with was phi. You guys remember, huh? Phi multiplied by dphi dt. Dphi dt is equal to phi point. Yeah, dphi dt is equal to phi point. And then dv dphi. As I told you, you have this, you have that, you have u, you have v, and you have minus u. So when we derived u par rapport à phi, we were rotating u 90 degrees into v. So this time now, we're deriving v par rapport à phi. So it's like we're deriving v 90 degrees. So not deriving, but rotating it 90 degrees. So rotate it 90 degrees and it's going to become minus u. So the derivative of v de phi is going to be equal to minus u. Comme ça, minus u. So when you derive this, you first derive phi. It's going to give you phi 2 point. Ah, sorry, no. Phi point. Phi point is constant. You guys know why phi point is constant, huh? Je m'excuse pour ça. Yes.
No, not so sure.
Phi point is the angular vitesse. Okay? Because when you look at the figure, yeah, so that's what you wanted to say. Yeah, when you look at this figure, this is, they've told us that this is rotating like that. It's rotating like that. So it's rotating with an angle phi. That means the angular vitesse is phi point. And we've been told angular vitesse constant. That means phi point is constant. Yeah, so these are the small things that confuse people and that cause you to lose marks. So phi point is constant. Phi point is a constant there. So this entire term this side, L plus R for phi point is constant. So we'll just be deriving V. So we'll have dV dt, and dV dt is giving us phi point moins U. So the final answer is going to be negative this side, phi point carré, because you have a phi point there and you have a phi point there that's coming from this expression. It's going to be phi point carré fois L plus 1 suivant U, like that, suivant U, comme ça. So that's going to be your gamma de OA dans R. So what's left now is just calculating this. This shouldn't be difficult. So you have omega K vectoriel A euro. So you get your constants like that. If you want, you can just get your constant omega, you multiply them, gives you omega carré, and you also multiply it by this other, so you get A omega carré. Then K vectoriel euro. K vectoriel euro will give you E theta according to our question. So we'll have E theta. We'll have E theta coming out there like that. E theta there. And then now we'll have K vectoriel E theta. K vectoriel E theta, you're going in this direction because you have euro, you have E theta, and you have K there. So now you're doing K vectoriel E theta. So it's in the anti-clockwise direction. So it's going to give you minus euro. And that's why we have this minus here and we have the euro. So the answer is minus A omega squared, because you have omega times omega squared suivant euro, because K vectoriel euro will give you E theta, and then K vectoriel E theta is going to give you minus euro. So you have minus A omega carré euro comme ça as your final expression for this double produit vectoriel. So your gamma d'entraînement is just going to be this gamma de OA, donc R. But this one is suivant U. We're not supposed to have answers like this. So you go back up to this diagram here. So at first we're working out V. Now we're going to work out U. It's just going to be the same principles. Okay, you just project a few things because you have your triangles there. So what you're going to do is, just if you want, just remove this V, just imagine it's not there, and then project this U up there. So project the U up there like this. This U, I've projected it there. And then I know this is 90 degrees. And I know the angle U is making with euro is theta. So that means U, euro will be theta like that. Okay, then opposite side is going to be sine. Adjacent side is going to be cos. Like that. So now I'm getting from the tail of U to the head, from the tail to the head. So from the tail, instead of going like this directly, I'll go like that and then like that. Like this, then like that. But notice this, I'm not going in the direction of U theta, I'm going in the opposite direction. So this is going to be minus sine over E theta, because I'm going in the opposite direction of E theta, and then here I'm going in the right direction of euro, so it's going to be plus cos theta of euro, and this is the expression that you find when you come here. When they worked out U, it gave them minus sine theta E theta and cos theta euro, like we found there. So it's just projections and all that stuff. So let me just erase this bit. As we quickly go through. Yeah, so which is what they got here when they worked out U like that. So you just expand this and then you simplify. You group the like terms, those following euro and those following E theta, and you get your final expression as this one for gamma E. Then you come to gamma Coriolis. The formula is always there, c'est toujours là, c'est 2 oméga de R1 par rapport à R vectoriel V. As usual, V is supposed to be a vector. I apologize again. I didn't know what I was writing. Yeah, so V test relative, we calculated it in the first question. It gave us A theta point E theta. And then omega, we know is omega K, so 2 omega K. Then the scalars, we can just get them. So it's going to be 2A theta point omega K vectorial theta is minus euro. We already did this in the above question. That's why it's given us minus 2A omega theta point euro as our gamma Coriolis. Then the final question, the third and final question, is asking us now to calculate the vitesse absolue. So the vitesse absolue, you just add vitesse relative plus vitesse d'entraînement. You add them, you group like terms and simplify. It's going to give you that. Then gamma absolue again, you just get, you add your gamma relative, gamma d'entraînement plus gamma Coriolis. Then you group like terms and you simplify and you get your final answer as that there. And that's that about exercise 5. Are there any questions? So you see from mechanics that it's just formulas in your books. Has there been anything new, anything foreign, anything you guys have not seen? No, it's just been the things in your books, in your polycopy, the formulas, the principles and all that stuff. It's just the differentiation and the trigonometry, which I told you guys to do if you haven't done them before, because those are the only new things you'll be seeing. Otherwise, the rest of the stuff, it's the things that are already in your polycopy. So if you read your polycopy well, you read through well and understand. Where you don't understand, you can ask your friends, you can ask me, you can ask YouTube, you can ask Google. There's answers literally everywhere around you. You will find them if you look for them. It's just things in your book. So revise, I emphasize, just revise this stuff. It's simple stuff. And the thing about mechanics is all about cinematic. The rest of the stuff, you'll be applying this same stuff, because from here, you're going to learn dynamic du point. Dynamic now, you'll be learning about forces and all that stuff. And you know the force is equal to what? Mass times acceleration. So for you to even calculate the force in the first place, you will need to be able to calculate the acceleration. Anything else that's going to follow. From that, you go and do energy. Energy, you look at things like kinetic energy. Kinetic energy is equal to half mv squared. V there is the Vtes. So for you to calculate the kinetic energy, you need to know the Vtes. You need to calculate the Vtes. So almost every question, every exam question is going to begin by asking you to calculate the Vtes and acceleration. So you're first going to need to locate m. You need to find out vector of position. Then you calculate the Vtes, calculate the acceleration. Then other questions like forces and energy and whatsoever else you'll be doing Mécanique du poids will follow. So cinematic is the backbone. Okay, it's the base, it's the foundation. You understand cinematic very well. You're able to do Vtes, you're able to do acceleration, you're able to do rotations, you're able to identify le repère absolu, repère référentiel, et tout ça. You can even get 20 out of 20 in mechanics without any problem. So it's easy for you to get a very, very high marks in mechanics. If you just revise the stuff, you understand it well, you apply your core very well, you get techniques from the TDs, how to answer exercises, you get how your professor is answering them, the tricks they are using, the les astuces that they are using, you use those things. You will see just how easy this module is going to become. It's going to confuse you, you're blank. You're asking yourself where this is coming from. You're wondering what they did there. You're wondering where to start from. That's if you don't revise. But if you revise, tout ira bien. Vous allez voir. So just go through the stuff. Go through the stuff. We're done with mechanics for me. For the summer lessons, this was the last part, the TD, the last question. At least I've answered 3 questions with you guys in cinematic. At least that should put you dans le bon voie. And from there now, since you know the direction to go in, you can pick it up from there and you can continue on your own. C'est compris?
Oui, tout est compris. So, Charles,
Yes.
does that mean from here, the next topic is going to be now dynamics, where there are forces and all?
Yeah, that's it. That's the next chapter. It's dynamic du point.
So from what we've done here, this is everything for like this first part.
For cinematic, yes, that's all you need to know.
Wow.
Even if a test was to come, like you said,
On cinematic, you can even get everything if you've understood this.
oh, then the questions, maybe if there are 4 questions, all of them they will start like regulate the vitesse, the acceleration.
Ashta?
Like you said all the 4 questions. Maybe if in an exam they give you 4 questions, each question will start with vitesse, then acceleration. So
Yeah, they begin with those things almost every time. Vitesse, acceleration, and then you go on because those are the base. That's the base. For you to calculate anything else this side, you need acceleration and the velocity.
d'accord. C'est clair. Oui, je comprends.
Okay. Good day, guys, and all the best in Mécanique du poids. I'm expecting you guys to validate with high marks. I only congratulate those who get above 15. Maybe I might even take you for tacos as a proud teacher.
Oh, gee.
If you get below 15, don't even text me.
Tapadi uboga mwirasa kamani.
Okay, guys. Kuya paso. Kuverenga fe ni finefe. Ifinefe na mpira fe. Mchai mfet ma question temofuti. Mle yako pa Google, search for more exercises with solutions. You try them and you try to compare your answers. You learn more. As I told you, it's about the tricks they use to solve. I haven't given you everything here. There's other tricks you need to use when solving. So the more questions you solve, the more tricks and techniques you learn. Just like that. That's how you're able to answer exam questions. Okay?
Yeah.
But be ready for more questions because when going through this, we'll ask again.
Okay, so now just revise. That's what I want. Yeah, I'm happy when people are asking questions. It means they're revising. Okay, I'll end the call now.
Thank you very much.
Thank you.
Merci
Yeah,
beaucoup.